We're about to go on this wild cosmic journey to tackle one of the biggest, most fundamental ideas about our universe. It's an idea that answers a question you've probably wondered about.
How do we actually know the universe is expanding? I mean, think about it. From our little rock floating in space, how could we possibly figure that out? It sounds like something straight out of a movie, right? But what's amazing is, it's not. It's something we can actually measure.
And the answer, well, it's not some crazy, complicated formula that only a handful of people understand. Nope. It's actually this beautiful, almost elegant relationship that was hiding in plain sight, in the light from faraway galaxies. This is where we get to the heart of it, the story of Hubble's law.
Okay, so let's get right to it. What is this law? What did Edwin Hubble, and, we really have to give a shout out to Georges Lemaitre here too, what did they figure out?
This is it, the big one. The law that completely flipped our understanding of the universe on its head. It's officially called the Hubble-Lemaitre law, and what it says is just wow. It's this simple, direct link between how far away a galaxy is and how fast it seems to be racing away from us. Okay, the best way to picture this is the classic balloon analogy. Imagine you've got a balloon with a bunch of dots drawn on it. Now, as you blow up that balloon, what happens? Every single dot moves away from every other dot, right? And here's the kicker. A dot that's way on the other side of the balloon is going to look like it's moving away way faster than a dot that's right next to it. That's it. That's our universe, in a nutshell. So to figure all this stuff out, astronomers needed some serious gear. You can think of it like a cosmic detective's toolkit, right? These are the tools that let them measure things that seem totally unmeasurable and connect the dots using clues left behind by starlight that's been traveling for billions of years. And at the heart of that toolkit is this formula. Don't worry, it's pretty straightforward. V equals h naught times d. So V is just the speed the galaxy is moving away, d is its distance, and that h naught, that's the magic ingredient. That's the Hubble constant, and it's the piece that connects everything together. Okay, but how in the world do you measure the speed of a galaxy millions of light years away? Well, the biggest clue is something called redshift. You already know how this works, even if you don't realize it. It's just like the sound of an ambulance. You know how the siren sounds high-pitched as it comes towards you, and then the pitch drops way down as it passes and moves away? Light does the exact same thing. As a galaxy moves away from us, its light gets stretched out, and that stretched light looks redder. That's redshift. And just for the record, the opposite is called blue shift. If something were moving towards us, its light would get squished and look bluer. But here's the mind-blowing part. When we look out at distant galaxies, pretty much everything is redshifted. They're all moving away from us. So let's get back to that h naught, the Hubble constant. This isn't just some number pulled out of a hat. It's basically the universe's expansion rate. It tells us how fast things are expanding for a given distance. And trying to pin down the exact value of this constant, oh man, that's one of the hottest topics in cosmology right now. It's a huge debate called the Hubble tension, and scientists are really going at it to figure it out. Right, and you probably saw that weird unit in the formula, MPC. What is that? It stands for megaparsec. I know, it totally sounds like something from Star Wars, but it's a real unit of cosmic distance. And it is huge. 1 megaparsec is about 3.26 million light years. We have to use numbers that big just to make the map of our universe manageable. That's the kind of scale we're talking about here. Okay, so we've got the law, we've got the toolkit. Let's actually use it. Let's put on our detective hats and solve a real cosmic case, finding out just how far away a galaxy is. All right, here's the file. Clue number 1. We look at a galaxy and measure its redshift. That tells us it's moving away at 1,000 kilometers per second. Whoa. Okay, step 2. We pull out our tool, the Hubble constant. For this example, let's just use a value of 60. Then we just plug those numbers into our formula, we do a tiny bit of rearranging, and bam! The answer pops out. That galaxy is 16.7 megaparsecs away. That's over 54 million light years. It's that simple, that powerful. But, it can't always be that easy, right? In the real, messy universe, things get a little more complicated. Hubble's law is an incredible tool for measuring really, really distant things, but it gets a little less reliable for galaxies that are, relatively speaking, in our backyard. Yeah, there are a couple of things that can throw a wrench in the works. For one, galaxies aren't just sitting still. They're moving around on their own, kind of drifting through space. On top of that, you've got gravity. Big galaxies pull on their neighbors, and that can mess with their speed. A perfect example is the Andromeda galaxy. It's actually moving towards us. So, for things that are close by, these local movements can kind of hide the bigger picture of the universe's expansion. Okay, this is where we zoom out. This is where it gets really, really mind blowing. Because Hubble's law doesn't just tell us, hey, the universe is getting bigger. No, it's so much more than that. It's like finding the blueprint for the entire cosmos. That number, the Hubble constant, is basically the Rosetta Stone of cosmology. Think about it. With this one number, we can literally hit the rewind button on the entire universe. We can figure out how old it is and how big it is. It's all packed into that one constant. So, here's the first jaw-dropping takeaway. If you take that Hubble constant and basically flip it upside down, you get something called the Hubble time. And that's an estimate for how long the universe has been expanding. The answer it gives us? About 14.4 times billion years. That's it. That's the age of everything. And that leads directly to the next amazing thing. If the universe is 14.4 billion years old, then the farthest light we could ever hope to see has been traveling for, well, 14.4 billion years. That gives us what's called the Hubble length. It's the size of our observable universe, a bubble around us that's 14.4 billion light years in every single direction. And of course, if you have a radius, you can figure out the volume. That's the Hubble volume, the total amount of space within our cosmic horizon. It's the whole shebang, everything we can see. Just pause and think about that. It all started with noticing that the light from faraway galaxies was a little bit redder than it should be. From that one simple observation, we figured out that the universe is expanding. And from that, we were able to calculate its age and its size. It's got to be one of the most incredible detective stories in all of science. So that just leaves us with one last question that will probably break your brain a little. Let's go back to the balloon. If the universe is the surface of that balloon and it's expanding, what's it expanding into? What's outside the balloon? That is a question that astronomers and physicists are still wrestling with. Something to chew on. Thanks for coming along for the ride.